Okay, this is Team 15's Project 3, which is a Mars Rover suspension system. Following members here for Mechanical Design 2017, Fall of 2017 class. Let's get started here. This is just table of contents showing a brief overview of our presentation. Okay, so there you go. Introduction. I said before, we're designing a suspension system for a Mars Rover, and we're giving a factor of safety and make sure that it's resistant to our static and fatigue failure. So, some of the things we have to go through is find first the forces, reaction forces, and the location of the maximum stresses in the suspension. Make sure, check for yielding and everything with the initial dimension guess. Afterwards, by obtaining that, we'll be able to optimize the design, make it lighter, smaller as possible. And here are some of the assumptions that we make. You'll see a picture of the suspension system right now, but we're assuming that the angle between the shock and the tube, it does not change, so it just stays constant throughout. Obviously in a real suspension system it might change a little. We're also assuming it does not deflect, so small strain. And another assumption that we made was that the forces that are reaction forces that are created in the x direction do not affect our design. See a little more about that right now. And also we're not taking into account environmental factors or the condition of the material itself, such as surfaces. We're assuming it's a perfect condition. This is a little visual representation of the suspension system. You can see the angle between the shock and the tube, and we're told that the tube we're using is a standard hollow tube. Right there, the second picture. So this is our free body diagram. As you can see, it's held by pins at the two ends, so we know that the reaction force that is created there on both sides. And the pins obviously have reactions in both the x and the y directions. And from this free body diagram, we're able to solve. These are our unknowns and our knowns. So we know we're giving a design life of 500,000 cycles, and we're giving a maximum load of 850 pounds. So initially we ran all the calculations with a 1-inch the outer diameter pipe. Got to the end of it, realized it was below our factor of safety, so we went ahead and upped it up to a 2-inch diameter pipe with the 1/8 inch wall thickness. We're also given that our maximum is at zero, our minimum is at 0, and the dimensions, the length of the entire bar, and the length between the force and the right side of it, and also obviously the material properties. We know tensile and yield strength. Okay, so from that, summing our forces, this is just solving for the reaction forces. And like I said before, we assume that we're assuming here that in the x direction, it's divided evenly, the forces on the x. So we didn't really take that into account for our design. We were more interested in the forces, in the reaction forces in the y direction, which you can see right here, what we get for pin A and pin B. So from that, we're able to draw our shear and moment diagrams. You can see that on the left is a shear at a maximum shear at 547 pound of force, and then the moment we see our maximum occurs at 2189 pounds force. So in designing, you see later, I just rounded off to an even number, rounded up, just extra precaution, I guess you could say. In order to get our modified endurance limit, we know we have to get our modification factors. We use a surface and a size factor here, depicted by the Ka and Kb. And with that, and knowing our unmodified endurance limit, which is just 0.5 of the ultimate tensile strength, we're able to get our modified endurance limit here, which is 23.25 KSI. From that, after that, we know we can obtain our normal bending and shear stresses shown here. Just plugging in. Like I said before, on the moment I went ahead and rounded up to 2190, just a little overbearing, I guess. And then here's the area and the moment of inertia, which we did both calculate from, which is not shown here, and also a table in the book provided them for us, so that is why we're just using the values given here. And with that, we can get our von Mises stress, and since we know that the minimum is at 0, we could it'll cancel out, so your von Mises stress ends up just using the maximum and the shear. And this is what we obtain here. Balmy stress is 7,214 psi. Using all that, also solving here, as you can see for our average stress and stress amplitude, we're able to determine our factor of safety. Also using dimensions and moment of inertia of the material. We end up obtaining a factor of safety of 4.69, which is above our factor of safety of 3 that we had to meet at least. And knowing that and knowing our von Mises stress, we're also able to obtain our factor of safety for yielding and for fracture. You can see all the factors of safety are well above our threshold 3. So here's just to obtain our S1000 here. You can see using the ultimate tensile strength of 90 kpsi, we obtain the fatigue strength fraction of 0.86. Okay, after that, now knowing our factor of safety, which is 4.69, and given our design life of being able to perform for at least 500,000 cycles, we're able to determine our actual cycles till failure for fatigue, which we ended up getting as 2,345,000 cycles, which is well above, the minimum requirement. So in conclusion, first we use statics, obtaining free body diagrams, reaction forces, all that, and then we mechanics of materials, little shears, and shear moment diagrams, as well as locating maximum stresses, and then we use mechanical design to obtain our more optimized dimensions, which would meet our required factor of safety and also not be a little over designed to where it's too big for our intended purpose or anything like that. So like I mentioned before, we initially started with a 1-inch outer diameter with a 1/8 inch wall thickness. After we solved for everything, we realized it was under our factor of safety, so we had to go up to 2-inch outer diameter with same wall thickness, and it was still reasonable. 2-inch diameter tube isn't overbearing or anything, so we're happy to just stick with that. Some of the challenges, obviously finding time, working together, but one of the things that really was a little iffy was the forces on the X direction. We were assuming they should have an effect, but with the assumptions we made, they weren't taken into consideration here. And that's our project. Thank you.